If we want to start with the graph of y equals x and match this graph represented by the green dotted line, as we mentioned before, we can stretch this graph by a factor less than 1 so that it comes down to match the red line, and then we can shift it vertically to match the green line. That isn't overly difficult to see geometrically, and we want to think geometrically here, but let's look at what this does to the equation of the function, or the definition of the function. We take y equals x, and let's say we do stretch it by a factor of 1/3 in order to match the red dotted line, which is parallel to the green dotted line. Then our function would become y equals 1/3 x, because we've multiplied all the y's by 1/3. Each point becomes 3 times closer to the x-axis, or 1/3 of its original y value. We can then lift every point here 6 units. We estimate that 1, 2, 3, 4, 5, 6 units are required to raise the red graph up to the height of the green graph. When we do that, we've increased the y value of each coordinate by 6. So we started with y equal to 1/3 of x, and we've added 6. So now we have the graph y equals 1/3 x plus 6. It should be clear that we can do this to match any straight line graph except a vertical one. Okay, what would we stretch this thing by to make it completely vertical? We'll never get completely vertical by multiplying by any real number. You can think about that. It should be clear that when we multiply the y equals x function, which we say has a slope of 1, that is 1 unit up for every unit over, we go over 1, we go up 1. When we multiply that by 1/3, the slope becomes 1/3. If we go over 1, we go up only 1/3. So that this number in front of x is the slope. In the general linear form of a function, y equals mx plus b, m stands for the slope. That's the number that we multiply by x, and we can think of that as our vertical stretch factor. And then we add b. That corresponds to raising the graph by b units. That incidentally raises the point at the origin, the point at which the graph meets the y-axis, by 6 units to the point 0, 6. So it turns out that if we raise the graph b units, 0, 0 is going to raise to 0b, and we're going to have y-intercept 0b, so that this is the y-intercept, and this is the famous slope-intercept form of a straight line. We can graph 2 basic types of families. This graph represents linear functions that all have the same value of b, which means the same y-intercept. You notice that we go through the y-axis at the same point for every graph, with m being variable. So m varies, b remains the same. M being the slope, we have every possible slope through this point, and we draw a few representative slopes to indicate the range of possible slopes. If we have the same m with b varying, b is the y-intercept, so that we go through the y-axis at different points, but with lines that always have the same m or the same slope, so all those lines are going to be parallel. So this would be the constant b family, a typical constant b family for some value of b, and this would be a constant m family.